So 24 is Newton's second law. Now let's say in the formula sheet it's written just as F equals ma, but I tend to write it as fun equals ma. Just because physics is such fun. So fun stands for unbalanced force. And remember, that's the same sort of concept as resultant force. M is mass, standard unit of mass, kilogram. And A is acceleration. Standard unit is meters per second squared. So usual example to go with that. You have a car of mass 800 kilograms, accelerating at 3 meters per second squared. We're asking you to calculate the force for that. So usual approach to problem solving. What am I told in the question? And what am I asked? Now there is only one force, it's just saying calculate the force. So this is like the simpler examples. So our formula is fun equals ma. It's just 800 times 3. 2,400 newtons. So we're going to do an example for this one. It's no new knowledge. It's just based on the work that we did yesterday. We've got an engine force of 3,000 newtons and drag of 800 newtons. We need to know the mass of the car as well. Similar sorts of numbers to yesterday, right? The mass of a normal car would be 800 to 1,200 kilograms. Now, one thing that's often included in the question in these, but can really make a big difference to solving force questions, is just a simple sketch diagram. Now, I'm not even talking about making it look like a car, but just clarifying in your own head what direction all the forces are acting. Now, these actually have a name. They're called free body diagrams, and that you isolate the one object that you're interested in, and then simply have arrows to represent all the forces that are acting on it. So in this case, I'm going to represent the right as being the direction of the engine force. The question hasn't specified that, but I'm going to call that my positive forces when we get to that in a wee second. And then drag, remember, by definition, will always oppose motion. Friction always opposes motion. And I've written the wrong number. I'm not having a good day. 3,000 newtons for the engine force, 800 newtons for the drag. Notice the arrows are attached to the object as well. That's quite important if you're asked in exams to sketch the forces acting on an object. They don't like kind of arrows floating in the air beside the object. They like them to be in contact with the object. And then we can start listing, right? The diagram helps make a difference to how we do our listing. So the simple number we've got, first of all, is a mass. What we want is the unbalanced force. And in this example, the unbalanced force is the engine force. Take away the drag. I'm going to call drag forces R for resistive forces. So Fun is E. And here's where I'm indicating that that's the opposite direction. So I'm calling the engine forces a positive direction, the drag forces, the resistive forces, as negative. So in terms of numbers, that's quite straightforward. But that's the only difference really between these examples and the ones that you were doing yesterday. So you've got to work out that unbalanced force. And now we can use that to work out the acceleration. So our formula we met yesterday, Fun equals ma. Rearrange. So just swap sides first of all, then divide both sides by 1,000. And we get our final answer. Okay, so another example, still on learning outcome 25. So we're dealing with more than one force, but this time they're not in one dimension, we're dealing with 2 dimensions. Okay, so this is bringing together a few bits, different bits of the course. So looking at adding vectors and using the Fun equals ma, the Newton's second law that we introduced yesterday. So once again, let us say for any force question, it's useful to start by drawing a diagram. So if you've got your golf ball, we know we've got 30 newtons pushing it north. I'll put a wee north line in, just so I know in my diagrams where north is. And at the same time, we've got 10 newtons pushing it west. Now, can we go ahead and get a resultant force from the diagram in its form it is just now? Why not? Not the right phrasing. You've probably got it right in your head. They're not nose to tail is the phrase we normally use. So one of them must start where the other one finishes. So you've got to redraw these, work out a resultant, right, okay, and then use that to get the acceleration. So it doesn't matter which one I pick first, but we'll probably find it easier. I do tend to pick the bigger one. Doesn't actually matter. But if I draw my 30 newtons north, then I have to draw my 10 newtons starting from where that one finishes. Now I'm not drawing this as a proper scale diagram. It's a sketch which will help me get the resultant. I'll stick to one colour because that's generally what you work in. The resultant, remember, is a single force that takes you from start to finish, but I usually put a double arrow on that to indicate. And I'm also going to mark that angle in there as X. So remember, a resultant force must include a direction. Right? And the simple 1D ones, it can be, the direction can simply be positive and negative. But in this case, we're going to have to work a wee bit harder. So using our Pythagoras first of all. Okay, adding the square of both sides. So A is the square root of 1,000. It's 31.6 newtons. And tan X is opposite over adjacent. 10 is opposite. 30 is adjacent. And tan X is 1 over 3, so X is tan to minus 1. You can still write it as 10 over 30 or 1 over 3. So we've now got a resultant force, and for our F equals ma, then that becomes the unbalanced force. And I'll put it in as, oh, in fact, that's not a bearing. Very quickly, to work out a bearing, are you happy that you'd actually have to go, use a different colour for this, clockwise from north would be that way round. So it's actually 360 take away 18. Okay, so the bearing is 344 degrees. And you can write bearings in brackets, or you could write the word bearing. We know the mass is 0.2 kilograms. And we've been asked acceleration. Now, just like when we did velocity as displacement over time, we don't put the angle into the calculation, but the acceleration will have the same bearing as the unbalanced force, in the same way that velocities had the same bearing as displacements when we did the v equals s over t calculations. So in our formula, fun equals ma. We just put in the magnitude of the force and then rearrange again. 0.2 times A is 31.6. You don't need to put all these steps in. If your algebra is quite good, you can go straight to these kind of final steps, but make sure you put in the first two, the formula and the substitution. And then divide both sides by 0.2. I'm just about running out of room here, and you get the final answer. Quite a large number, okay, but you probably will find that for that short instant that you're hitting the golf ball, you get a very large acceleration. Right? We're not saying it continues to accelerate once you stop hitting it. And we've got to copy it over the bearing, but bearing 344 degrees. Okay, so I've put the wrong bearing in, because I subtracted 18, it should be 342. Learning outcome 26. But it is still based on Newton's second law, and it's basically applying Newton's second law to space travel. Now, Out in space itself, that's actually quite straightforward because there aren't many forces, there's no drag. You might have a wee bit of weight, but generally we don't ask you about that. So pretty much at that point, if you put on the thrusters of a rocket, then you've got one force, and that is your F in the F equals ma. But during takeoff, this is much more common when we look at past papers. Okay? So once again, we're just going to do another example to familiarise you with the types of questions that might come up. We do tend to ignore the air resistance. Often we ignore the air resistance because the question has a phrase in it like at liftoff, which means just at that point where it's about to start moving but isn't quite moving. Now, if it's not moving, it's not going to be experiencing air resistance. So at that point, the forces are a wee bit simpler, but we'll see exactly which forces. So during takeoff, or at liftoff, maybe actually doing a better phrase there, but I'll leave it as it is. A rocket accelerates at 4.5 meters per second squared. It has a mass of 20,000 kilograms. And just like with the car, we gave that force a name. We called it the engine force, right? The name from the rockets of a spacecraft is called thrust usually. So calculate the thrust of the rocket engines. Now, once again, it's really important that you draw a diagram, sketch the forces, establish what the unbalanced force is in this case. So once again, I'm not making it look like a rocket. I'm just going to recircle. I don't actually need to put the mass in of it on the diagram. So what forces do we know about? Well, it mentions thrust in the question. What direction would the thrust be acting during takeoff? Upwards. Okay, so we can put in an arrow for the thrust. We'll call that T for thrust. Right, and we know that's what we're actually being asked in the question. We don't know its value yet. Are there any other forces acting? Okay, so let's assume that the question's made it clear that you can neglect air resistance. Are there any other forces acting? Weight. So notice it hasn't mentioned it anywhere in the question. But you have to recognise that in any example where something's moving up or down, then weight's going to be a relevant force. It's okay for the car where it's going along a flat road, weight's not relevant there. But for any situation where something's going either up or down, then even though it's not mentioned in the question, you've got to remember to include it. So we're going to have to include the idea that weight tries to pull it down. Because it's very easy in that question to look and say, oh, look, I've got an acceleration, I've got a mass, F equals ma. Right? We are going to use that in a wee second, but we need to see that's not the same as the thrust. Right? So in this case, the unbalanced force is not equal to the thrust because there's two forces. What we can say, though, beside our free body diagram, is that the unbalanced force is equal to, even without knowing any values, right? So for the car, we did it was the 3,000 take away the 800. Anyone want to have a go at what that would be in terms of the letters that we've got in this example? It's saying the unbalanced force is the upwards forces take away the downwards forces. Okay? And I doubt you would get more than two forces in any problem. If we were including drag, then drag would also be a downward force at this point because the rocket's moving up the way. But, so we've now got an expression for fun is equal to T minus W, but we also know that fun is equal to ma. So now we can use both of those ideas together. Right? So if I go to list my variables, I've got that mass is 20,000. I've got the A is 4.5. So when I write my formula now, fun equals MA, and I replace what I can. So I can replace fun by T minus W. And I can substitute in M and A. But if I'm going to work out a value for T, I'm still missing a value for W. So I need one more formula. Now usually in an exam question, this wouldn't all be one big question, it would be bits. So part A might be work out the weight. Part B might be work out the unbalanced force. Okay? But I'm going to have to do a calculation of W. Don't know what it is, but we do know that W is equal to mg. Right, we're assuming it's on Earth because it hasn't mentioned any other planet, but you could apply it equal to other planets. But we can do our 20,000 times 9.8. Calculator out. That's 196,000 newtons. So now I can substitute that into my question. I can do the 20,000 times 4.5. And now I've just got simple rearranging to get the answer for T. So I'm going to add 196,000. Notice it's not a multiplier dividing here. I'm going to add 196,000 to both sides. That leaves me T on the left-hand side. And do my calculation. 286,000 newtons. Strictly speaking, specify the direction upwards. And basically what we're saying here, right, is that the unbalanced force is 90,000 newtons, but to provide that, the rocket has to provide the weight. It has to balance out the weight first of all, and then provide another 90,000 newtons on top of that. So it has to provide the 196,000 to counter the weight, or else it's not going anywhere. And then add another 90,000, and that's where we get the 260,000 newtons upwards.